All right, these are the answers to page 685. We're building out a Maclaurin polynomial for something a little more complicated. And so what we do is we say, well, what would be the original, what would be the simpler version, which in this case for e to the x would be 1 plus x squared over 2 factorial plus x to the third over 3 factorial, and then it would keep going, right? So what have we changed? Well, instead of x, we have x squared over 2. So our Maclaurin polynomial would be 1 plus, now not x, but x squared over 2, not x squared, but x squared over 2 squared over 2 factorial. Not x cubed, but x squared over 2 cubed over 3 factorial. And that would keep going, right? And then we could actually work this out if we wanted to kind of see what that looks like. We could write a general term for this, which eventually we probably would have to do. As far as the general terms, we can do it one of two ways. We can say, well, the general term for this is x to the n over n. So we're just going x squared over 2 to the n over n factorial, right? And that would be okay, and then we could even work that out a little bit further and write it as x to the 2n over 2 to the n factorial. That's just bringing the n to both of those and writing it like that. So that's your general term for that one. Sometimes they'll require it, sometimes they'll just ask for the first few terms. The good thing, again, is that we can use what we know about e to the x, which is simple enough, and just replace x with whatever's up here. Same thing with a sine function. If we know that sine is x minus x to the third over 3 plus x to the fifth over 5, and so on and so forth, then we can just simply put 3x in place of that. So g of x, its Maclaurin series would be 3x minus 3x cubed over 3 factorial plus 3x to the fifth over 5 factorial minus, and then we can keep that pattern going. Okay. And then if we wanted to, there's a kind of an odd general term for that. They usually don't ask you for that for sine and cosine, but we kind of see this pattern forming here. Same thing with the cosine. We know that cosine by itself is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, and then so on and so forth. So we can do that same idea here. This function's Maclaurin polynomial would be 1 minus x to the 3 halves squared over 2 factorial plus x to the 3 halves to the 4th over 4 factorial, and then keep that going, minus x to the 6 over 6, x to the 8 over 8, keep that going there. So that's all we're doing with these things here. And if there's extra stuff to be done, like if this had been this, minus 1, then we would have done all of this minus 1. Those 1s would have canceled, if that was part of it. If it had been divided by x, then we would divide all these terms by x individually. So we can just, no matter how complicated this function looks like, we can take a simpler version of it and just build it from there, which is kind of the nice thing about this. So when we have a combination like this, we know that e to the x is 1 plus x squared over 2 plus x to the 3 over 3, so on. So e to the negative x is the same thing, just we're going to put negative x in, which for the even ones won't change anything, right? A negative squared is positive still. But for the odd ones, we'll make it negative. So when we do that, what ends up happening is that these cancel when we add, I'm sorry, we're not adding them, we're subtracting them, my fault. So since I'm doing e to the x minus this minus this, the 1s actually cancel, the positives cancel, and I end up with x minus negative x, which is 2x, x cubed over 3 minus negative, so that's a positive 2x cubed over 3. And if we were to keep that going, I'm sure we'd have 2x to the 5th over 5, and 2x to the 7 over 7. So we get 2 of each of those going forward, but we're going to take half of that, and when you take half, all the 2's go away. So we end up f of x equal to x plus x cubed over 3 plus x to the 5th over 5 and x to the 7 over 7, and then keep going like that. So we can actually combine these here, see what happens when we do that, and then kind of work it out from there. Same thing here, we've got f of x, and on 37 we were asked to just come up with the first 4 non-zero terms. So if I put e to the x as 1 plus x squared over 2 plus x to the 3 over 3, that's probably going to be good enough there. And then the sine x, so this is e to the x, times sine x is x minus x to the 3rd over 3 plus x to the 5th over 5, and that's probably going to be good enough there. What we're actually going to do now is we're going to just do some multiplying. We're going to like FOIL this out. So our f of x function will be 1 times x. 1 times this would be negative x to the 3rd over 3 factorial. 1 times that, which would be x to the 5th over 5 factorial. Okay. Then let's move to the x. X times x will be x squared, and then minus x to the 4 over 3 factorial, plus x to the 6 over 5 factorial. Okay, then we go here. X squared times that would be x to the 3rd over 2 factorial, minus x to the 5th over 2 factorial, 3 factorial. We'll just write it like that for now. All right, and so we're trying to come up with the first 4 non-zero. Now we see we don't have a plain number, so x is probably going to be our first term. So we need an x squared, x to the 3rd, and an x to the 4th. Those will be our terms. So these x to the 5ths probably won't play a part in it anymore. And if I go to my last term here, x to the 3rd over 3 factorial times that would be an x to the 4th over 3 factorial. All right, so I did my first 3, then my next 3, then my next 3, and so now I'm doing that very last one, x to the 4 over the 3 factorial. All right. So now I'm ready to kind of look here and see what I've got. I've got x, we've got x squared, we've got negative x to the 3rd plus x to the 3rd, but they're different denominators. This is 2 and this is 6. So if I were to make this a 6 as well, I'd have 3 of these minus 1 of them. We're going to have 2x to the 3rds over 6, which is x to the 3rd over 3. And then our x to the 4ths, I've got this minus x squared. So I had this x times this, which gave me that, and then this x times that gave me a positive. This is actually going to cancel out. So I don't have an x to the 4th, so I do actually have to go to the x to the 5th now, which is kind of obnoxious, but that's okay. I think I only have these 2 here. I have an x to the 5th over 5 factorial, which is 120, and then I have this minus x to the 5th over 2 times 6, which is 12. So that actually is not too bad, because if I multiply by 10, now I've got negative 10 of them plus 1 of them gives me negative 9x to the 5th over 120, which if I divide by 3 gives me 3/40. All right. So a little bit of work. I had to multiply it out, had to kind of combine like terms, but these are our first 4 terms. 1, 2, 3, 4 of the Maclaurin polynomial for it.